Higher order functions. They can take functions as parameters and return functions. Yep. It's called a higher order function. They pretty much are the Haskell experience. All right. So you want to define what stuff is instead of defining some state. You're going to need higher order functions. That makes sense. Now, they're a really powerful way, apparently, of solving problems and thinking about programs. I know a decent amount of this. I know you can have, like, I don't know. Right, so I'm aware of this. With that said, allow me to open up the period functions. Every function only takes one parameter, so how is it possible that we have defined and used several functions that take more than one parameter? Right, like obviously add, if that is a function. Well, I could make my own. So add xy equals x plus y. So here's the thing, it just returns a new function. So when you do this, you're really making a new function called add7 and then putting 8 into that. The best way really to write it in JavaScript would be to do something like this. So it's like calling it like this, right? But if you only call it with one, it'll just return a new function. But in this case, you'll see here that B is bound. No, A is bound to 3, and then you'll end up just adding it to 3. So let add1 equals add1. You can do some really cool stuff like this. That's basically the essence of currying. Right, so this is the same as this. Yeah, this is the cool part. Performance-wise, terrible. You need a ton of compiler optimizations, but you know, it is still very, very cool. Mod 3, sure. Just obviously to do this, that's all good. But if I do 1, 2, yeah, simple enough. And you kind of get the idea already. This way that you're making new functions by not fully using up an old one. Right. These parentheses are right. So this is like saying something that takes an A and returns a function. That new function takes an A and returns a function, which takes an A and returns an A. So, yeah. Yep, exactly what it says here. And this is basically what I did. Mult 2 with 9. Yeah, and you can keep doing things. Mult with 18, and that'll just make another function. Only when you call that, because it really just takes one parameter and returns that A. So that's this part. Then it'll give you back your 180. What if we wanted to create a function that takes a number and compares it to 100? Well, you could do something like this, of course. But better yet, you can leave this part out. You're partially binding the compare function. So if you have compare, now you can just make a new function, let positive. Pretty much you could do this. And then you could do positive 8. doesn't really make sense how it's working here, but good enough. It's like me saying add 2 equals, instead of saying add 2 x equals. Make sure you really understand them. I feel good about this. Infix functions can also be partially applied by using sections. Yeah, so this is cool because you can do +1, and that'll just be a new function which adds to 1. So this could have just been +2, in fact. So add 2, and there you have it. To section an infix function, simply surround it right. So you've seen this before. Calling divide by 10, 200, is equivalent to doing 200 divided by 10. Right. Yeah, so this is also cool. You can do it like this. So that's also a thing. For some reason this was not before, because I feel like I defined it up here. Yeah, that was not a thing. So that's... maybe it's... no. Interesting. Right, so obviously it's not going to let you just print this because you're trying to ask it to print a new function, and that doesn't make sense. Functions aren't instances of show. So you can't really show them, you know? Right? And in fact, if I do this, I'll get lots of cursed stuff going on. The more I go, the less less usable it becomes. Functions can take parameters and return functions. Right, but in this case, you have got to use parentheses. Yeah, here they're mandatory. So you have now the classic function. Say I have multiply, right? Well, multiply is not a good example. The classic example is map. So map takes some kind of function and then some kind of collection and applies it. So if I do times 2 to 1 through 5, well, there you go. I mapped everything times 2. Now I'm going to write map myself, actually. This looks like it should be a bit of fun. Now, map will take a function, turns an A into a B, and it'll take a list of B, and it will return a list of B. It'll take a list of A, return a list of B. So, if you give it some function and nothing, obviously it should give you back nothing. If you give it some function and then you give it an XS, so some list, a list of stuff. Better yet, destructure it here. F of X perhaps I need a no? That's what I would think it is. Calling f1x, this takes an A and a B. X is an A, right? XS is a bunch of A's. Oops. XS is a bunch of A's, right? I was gonna bring up the wrong thing. With that said, This should work. I'm not sure why it won't. I'm going to put parentheses around both of these and see if something happens. I forgot. Yes, there we go. You're gonna have to give it back the function. And now it'll yell at me to use some like alternate foldel or map. Yeah, it'll tell me literally to use map because that's what map is, right? Uh, but either way. This should work. So if I can now do the exact same thing. Of course, I need to load the first. There you go. So basically just draw map. And then you have filter, which takes a function which turns an A into a bool. It'll take a list of A's and then it'll give you back a list of A's, but it's filtered, right? So again, if you filter nothing, you're getting nothing. If you filter F and then some XXS. So if fx, then okay, at least it's parsing. If it's fx, then it's that x, so that x gets to stay, as well as the rest of filtering. It's otherwise, if it didn't match, it's just filter fxs. That seems to be right to me. Filter, I don't know, filter less than 8, 1 through 100. And there you have it. Easy enough, right? Not too bad. So these are some examples here of higher order functions. These are the two classics that come to my mind. You also have reduce. I do wonder, there's like, they're called fold. You fold something into a bunch of things. So you have fold, right? Fold L or fold R, right? Is reduce a thing? No. So you have fold L, say plus 1 through 5. You have to give it an initial value, I believe. Yes. There you go. So you give it an initial value, and it'll deal with it. Now, I don't know the difference between fold L and fold R. In this case, the same. But so I think in this case, sum 1 through 5. So to the point where you could even say sum equals fold R plus 0. And then you could say product equals fold R times 1. And with that, that kind of explains why, yeah, that's pretty cool. And you have fold L1, which means don't take an initial value, just use the first value. So I'm not going to give this one an initial value. But the issue with that is if I give it an empty list, it'll fail, right? Because it doesn't know what do you get, what does it give you back? It doesn't make any sense. All right. Feeling good about this? Okay, let's make a function apply twice. We'll take some function a into b. No, actually the a will have to go into the same type, otherwise it doesn't make sense. And then it'll need to take an a, and it'll spit out an a. Right? Now apply twice will take the function and the value, and it will give you f of fx. There you go, word for word. Yeah, 10, right. But now I wonder, can you put that together with map? Yes, you should be able to. Let me do this. Times 2. And it works. You see? That's pretty cool. So I'm making a new function here using currying, which lots of things going on actually, but when I do apply twice times 2, I'm making a function that essentially multiplies by 4. And then I'm mapping all these values with that function. So it'll multiply everything in there by 4. Is this, by the way, a function? Neat. Neat. Oh, so this is the thing. Okay, so you can also call them like that, and that will change the order in which things happen, which I suppose usually is not useful, but in this case, obviously is, because here you're putting it before, and then here you're putting it after. So let me make a function called add exclamation. Takes a string, returns a string, right? Or better yet, I could just, that's pretty neat that you can just write it like that. That's pretty awesome. Just to make sure that's correct, add exclamation. Hello, right? And now I can do add 2 exclamations, which means dot. I'm a genius. Use dot, right, right, right. That is very nice. Oh wait, shoot. Couldn't this have also been f dot f? Right, so this is, I guess, a case where you actually do need a. Doesn't work? Huh. Well, in my case, it worked. Hmm. I cannot figure out for the life of me why that would be true. It feels like they should be able to do that, but I guess not. You have to do f of x, and you have to give it that x. Am I screwing something up? Oops. Oh, there you go. There you go. That's pretty awesome, actually. I wonder now, could you even... It'd be really funny if there was a way to make this even shorter, using the fact that you're... Because this itself is a function, right? So I'm calling this, basically. With that said, I don't think you can. I think it would be awesome if you could, but I don't think you can. This is still brilliant. I mean, this just like, wow. Anyway, I can now apply twice, add. Yeah, so that does not work. You have to do this. Oops. But maybe it did work, actually. Maybe I'm just not cooking. There we go. Yeah, all good. Can you even do this? And that's 4. And then if I do this, this will be 8. What? That's too many. Oh, it's exponential because you're calling that thing that many times, kind of. So if I did this now, I should get 256, and it's very slow, but there should be 256. What? Huh. That is really something. I genuinely don't know why. It went 204, 16, and infinity? I don't know. I genuinely don't know. That is something. That is really something. Okay. I guess that's what? How long have I been live for now? 20 minutes. Anyway, so it turns out you can also call functions like this, which is coolio. Okay, we're gonna call zip width. It takes a function and two lists and then joins the two lists by applying the function between corresponding elements. Ooh, that. Let me just see what the function does. I'm just going to go into Google, zip width. Let me just see how to use zip with comma. Wait, that's a thing? That's cool. Actually, that is kind of cool. I respect that. Okay, I see though. So it'll, yeah, fx1, x2, f. Okay, that doesn't seem too bad. Let me figure this out then. Again, I need to talk about what this does. It'll take a function which takes an a and b and turns it into a c. And then it'll take a list of a and a list of b, and using that function, it'll turn them, like zip them up into a list of c. Now, so you have your function, you have your ax, bx, I'm going to call it xs, ys. Right, so we need to talk about edge cases. If we have some function, empty list here, not, I don't care what's here, then it's an empty list. Same goes for if you have your function and an empty list here, that's still an empty list. Now, otherwise, otherwise both of them are non-empty. But you have your function, you have your x-axis, and then you have your ys equals. You have apply the f to the x and y, and then add it to the result of zipping the rest of it. I think that's it. Only one way to find out. So zip width. Now our function, let's just make the function comma, as was said earlier, 1 through 5, and zip it with 8 through 10. Seems to be right. Now let's zip it into a plus. I think that's it. 1 and 8, 2 and 9, and then 3 and 10. I think that's it. And here you have it. Pretty much what we wrote. Only difference is here they used underscore. Not bad. That's neat. That's neat. That really is. This is so much fun, honestly, like learning all this. I love Haskell. It's actually good. Oh yeah, and of course you can use T. Zip width. I'm pretty sure I don't even need the type here, and it's just smart. It's just genius. Look at this. Look at this genius mode. Brilliant. Obviously you don't need this. It'll still type check. It just won't work because it'll never stop. So then you have zip width plus. Oh yeah, these are all these things. Oh, zip width math, because that's a cool one. One through, well, that's not fun at all. I'll just copy these values. 7, 3, 2, 5. Yep. Oh, and then you can even do some cool zip width plus. Isn't this this is 3 lists. Oh, it's not. I'm dumb. This is the output. This is cool. Or better yet, you could just repeat 2 and then 1 through, I don't know, 10. So multiplying everything by 2. This is really just the same as map times 2, 1 through 10. Right? Easy enough. And you're telling me you can also do map 2 times. Same thing. But if you're doing division, it'll matter, because 2 over is very different from over 2. Just saying. Right. This is definitely like the best part of functional programming by far. Like it's everywhere. No, you see it everywhere. Flip takes a function and returns a function, but the 2 arguments are flipped. Okay. Okay. Flip f ab equals fba. Oops. And it can even figure this out, I think. It can look at this and say, oh, well, you have some t. Maybe I should use xy. And I'll rewrite this actually as a function which takes a into b into c. But you're giving it in the order of a into c into b. Or maybe I'm wrong. And of course, it needs to return the C. Or not. I'm not correct. You don't need the A. A is B into A. There we go. There we go. It's a bit cursed, but basically it's saying, taking some function which is going the normal way, right? A into B into C. And then I'm going to take the first 2 arguments but flipped. So instead of taking A and B, I'm going to take B and A. I'm going to apply it, and then I'll give you back the C that this function would give you back. This is interesting. You can double map something, really. So you're telling me that if I did map map plus 1. I could do it on some nested list, like 1, 2. Huh. Let me think about that. You're going inside, you're applying this to this whole list, right? And then that will map that list. That is pretty cool. That's pretty awesome. So zip with times will actually go and oh yeah, this times this, this times this, this times this. And if there's like any part that's missing here, like say I remove this, the last one will just have 2 elements. Right. Because that's what we defined. If any of these lists are empty, it'll stop. Oops. Okay, so we did flip. I wouldn't write it like that. I wouldn't use where. I don't think we need that. Oh, yeah, this would be a nicer way to write the type signature, wouldn't it? It's like saying, oh, well, I'm going to take this function and I'll give you a new function. But that's already kind of implied. That's the tricky part is you don't need those parentheses. It's already done for you. Same way I could, like here it doesn't make as much sense. But this isn't even true. You can't do that. So it's kind of backwards of what you'd think it is, whatever. Yes. This is what I wrote basically, like word for word. When I call flip f without the parameters. Yeah, I don't really care about that. Okay, flip. Zip that with hello. Yeah, so it'll flip it. Instead, it'll be as if you zipped hello with this instead of zipping it with hello. It'll flip them. What is this? 2, 2? Won't this just be 2's forever? So that's the same as repeating 2? Not sure if I enjoy that, but whatever. Of course, you get the classic, just thought I'd bring it up. I love that. Now we get map and filter. We did this earlier, so all good. Map, filter, yeah, blah, blah. Alright. Stretching a bit. This is more or less what I wrote earlier as well. I should probably stop calling things F every time. I should call it key. In this case, for predicate. Filter equals 3, filter greater than 3. Right. And you can do stuff like count filter. I don't know. How do you do that? Check whether something mod 2 equals 0. Obviously you can do this, but is this proper? I'm not going to do count. I just want to see whether this is proper. Apparently it is. Although at this point, I mean, just make it an anonymous function. I mean, come on. Just check whether x mod 2 equals 0. It just seems a lot nicer to me. Yeah, good enough. And this is 1 million values. Now, here's the thing. Let me take the length of that. That's fairly fast, so not really a problem. Now, obviously, this would take 10 times the time, but I can figure it out. Now, what if I were to do 824? It's slower or not? You should see it generally go down. Oops, yeah, that's infinite. Nothing? 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 Come on, this must be a lie. There must be some value that's... Oh, no, because it will always be an even number. I mean, odd number. This should give me some values. Quite a few, actually. It's quite fast. Alright. I just love playing with numbers. It's fun. So I can do lowercase equals and I can do filter lowercase of some silly string. So like this. Arg. No. Going back, going back, going back, going back, going back, going back. Better yet, not lowercase. And then you can go and do your actual lowercase if you want. Allow me. I could have just used the... I'm being dumb today. But yeah, pretty cool. Neato. And by the way, you can also make zip with next. So for example, of list at xxs equals zip list with xs. That should work. You got 1, 2, 2, 3, 3, 4, 3, 4. Yeah, pretty cool stuff. I like zip with next. It's a nice fun function from Kotlin, which generally works pretty well. I love filter. Oh yeah, quicksort. I actually ended up doing this. I used filter anyway, so well, I guess they're just waiting. Even if you map something over a list several times and filter it several times, now this is really strong. Like this is really good. It's like the iterators from Rust, except it's automatic, and you don't need a ton of syntax sugar to do it. Whereas generally with languages like Scala, I know, Kotlin, by default it'll go and turn. So for example, let me draw it out what I'm saying. So if you have some like 1, 2, 3 up to like I don't know, thousands, and you say, okay, well I'm gonna map +1. Now obviously syntax doesn't look like that, but it'll go and turn this all into a list of 2, 3, 4, up to 1001. And then if you go and tell it to do something else, it'll make a new list, and then it'll make a new list. Whereas with a more lazy approach, it will simply keep track of what it has to do. So this is true in Rust, for example. I can have a let me just really quickly play around with Rust. I can have a let range. So I can have a list of 1 to infinity, and I can map x to x plus 1. and then I can take 5 of them, right? Okay, it's gonna be a bit of a hassle to but anyway, you can see it got me my values, but it clearly never actually mapped the whole list because this list is infinite. It goes forever. And that's one of the strengths of this sort of thing, is that you don't even have to know how long something is. And you can still map it. You can still, as long as you're taking it, so it's called like an adapter function or something, it really tries to collect it. So if I tried to do sum, for example, well, that would never finish. Obviously, if I wasn't being weird with the types, it would never finish. But if you're doing certain things like taking the first amount or something, or taking until, or you're filtering even. No, not exactly that one. But for some things, uh, it's just better, and it's almost never worse if you can optimize it properly. Thanks to Haskell's laziness, it'll even do that. Let's find the largest number under 100,000 that's divisible by 300, 3829. 100, is this a number? Okay. 9 through 1. Right, so here's our backwards list. Now, we want to find in there 3829 equals 0. Now that's not a thing. Head of filter. Notice 99554. Yes, head of the filter. Exactly, perfectly done. And if I call this, well, it won't tell me what it is, I guess. 99554 was the answer I got. Take while. Oh, right, take while is also good. I guess. You could do it right. I mean, first equals head of filter. Or not. Really? It won't let me do that? Alright, you know what? I'm not gonna worry about it. That should work, I would guess, but whatever. Take while it's not equal to space, and it would return elephants. Whoa. The sum of all odd squares that are smaller than 100,000. Okay, easy. So, oops. First of all, squares are like this. Right, here are your squares. Now, we want to take while less than 100,000, and then I'm gonna want to sum that. And I should get, oh, the sum of all odd squares. Filter odd. Well, that seems also wrong. Oh, it's 10,000. I see. There you go. That's the right answer. Yeah, it does help to sometimes use those dollar signs. after this, I'll go. This seems like a good place to pause. Could have written it using list comprehensions, but I like this better. A lot better, a lot nicer. This is kind of a word. I don't like it. It seems weird. Only, yeah, again, it's not going to use this all up. It's going to just, it'll see this as like, okay, well, when I have to do it, I'll do that. And they'll see this as when I have to do it, I'll do that. When I have to do it, I'll do that. Only when you call sum does it start doing it. And it'll stop when it's done because of this take while. Alright, so I guess next time I come back, it'll be call out sequences. So that'll be cool. And we're already here. Hopefully I can finish it the next video and have some fun with this.